In this video, I'm going to be showing you guys how to find the total area using integrals. So, traditionally, with your integral, when you use the fundamental theorem of calculus, stated like so, where your upper bound is treated as an input into your antiderivative, and then you subtract the antiderivative with your lower bound as your input. Traditionally, when you have, let's say, some graph, and you want to define some area between the curve and the x-axis, using the fundamental theorem of calculus, you're calculating something called net area. So net area treats the areas under the x-axis as negative and the areas over the x-axis as positive. But the thing about total area is that you have to treat the negatives as positive areas. So you want to find the total area. You don't care about if the area is negative or positive or not when you're finding total area. And keep that in mind when it comes to the wording of problems. With the wording of problems, oh boy, you can get these wrong because all they ask is solve the integral, solve for the total area using the integral. And sometimes you're going to get that mixed up. When you're in an exam, you're stressed, you have no idea what you're doing, and then you forget to solve for the total area. You forget what that is. So total area, keep in mind, treats all the areas between the curve and the x-axis as positive. Well, how do you solve for the total area? Well, you're going to get some notation that looks like this from your class, where you treat the function as an absolute value. And technically this is right, but this doesn't really help you that much. It's really like it's kind of unhelpful because you can't calculate anything with something that looks like this, right? You're gonna have to separate the function into like piecewise functions now or something. Like, I'll just show you another way to do it where you use the concept of zeros to help you do this. So when you absolute value a function, every single negative part becomes positive. So if I were to just reflect only this interval over the x-axis, it would look something like this. And now your new graph looks like this, and you calculate the areas of these parts instead of the area of the negative part. But man, this function looks really weird, right? I mean, like, how do you write a function for that? Absolute value function doesn't help at all. So we're going to use like sign charts, kind of, in this video, and I'll show you how to solve for some problems right now. So for this problem, you're going to need to find the zeros, and I'll show you why you need to find the zeros right now. The zeros are going to be very helpful because they tell us when the function goes negative and when the function goes positive. So let's draw this function out. And I'll draw the bounds out, sort of. This is not drawn to scale, of course. But right now, we have our bounds -2 and 2. And it already kind of gives the hint that the zeros are within the -2 and 2 bounds of your integral. But the reason why we want to find the zeros is because, well, we know the zeros. When we can solve for these points, we can separate the integral into 3 regions. So we can solve for the integral individually with a region with -2 to the first 0, which is negative square root of 3. And so this is the negative square root of 3, and this is square root of 3. Right, that point has an x equals square root of 3. Let's be more specific here. X equals square root of 3. These are these points. And we can separate this region into square root of 3 and 2. So when we calculate the integral of just this region using the bounds -2 and negative square root of 3, we're going to get some positive integral because the area is over the x-axis in this case. But when we solve for the integral between -3 and square root of 3, negative square root of 3 and square root of 3 for our function, we're going to get some negative integral because this area is below the curve. So what we actually can do, well, as I already said, you can separate your function or your integral into 3 different integrals and just absolute value this area. So when you solve for the area between negative square root of 3 and square root of 3, you're going to get some negative area because the area is under the curve, or some negative integral. And when you do that, you can just absolute value it. And when you absolute value it, you get some positive area. So instead of calculating net area, you're calculating total area. So let's find the antiderivative of this first. So the antiderivative is x to the power 3 over 3 minus 3x. Using reverse power rule. So if we solve for this using three integrals, our first bound is -2 and negative square root of 3. And square root of 3 is one of the zeros of this function, one of the functions where it intersects with the one of the x values that where the function intersects with the x-axis. And when we set our bounds, -2 and negative square root of 3, we will calculate some positive area. So let's hope for that. So x squared minus 3 dx is equal to, and we're still going to use the fundamental theorem of calculus in this case, just for this section here. So let's use the fundamental theorem of calculus. We do plug in the upper bound into the antiderivative first, minus 3x. X is negative square root of 3 in this case for the upper bound. And we subtract the lower bound input into the antiderivative. So -2, 3 over 3 minus 3, -2. Now I did all the lousy arithmetic for you guys. But basically, our area between -2 and -3 is 2 square root of 3 minus 10 over 3. Plug this into a calculator, you're going to get some positive number. It's like 0.15 or something like that. But what we can actually do is, rather than solving the integral from the square root of 3 to 2 for our function, what we can actually do is, since this function is symmetric, we could just multiply this area by 2 to get 2x, to get both of these areas. That's kind of a little trick for symmetric functions. But if we just multiply this by 2, we get 4 square root of 3 minus 20 over 3. So let's save this, because this number right here represents the areas between the curve and your x-axis for these two regions. All right, one last thing. Let's go ahead and solve for the area between the curve from 0 to square root of 3. And the reason why we're doing 0 to square root of 3, which is simply just this region right here, is because, again, the function's symmetric, so we can just multiply it by 2 rather than having to deal with the negative square root of 3 bound. So if we plug in our integrand and then fill out our numbers for our integral, for antiderivative, we get square root of 3 over 3, square root of 3 cubed over 3, minus 3 square root of 3. And then if we plug in 0 to anything here, all just cancels out, so we don't need to care about the 0. Now, all this does is simplify to square root of 3 minus 3 square root of 3, which is just equal to negative square root of 3. Negative 2 square root of 3. And that makes sense in this case, since the area is negative. And we just have to multiply this by 2. So 2x to get negative 4 square root of 3. And this area right here is the area under the x-axis. So again, the reason why I multiply this 2 is because since the function is symmetric, we calculate the integral from 0 to square root of 3, we can just kind of multiply this area that we calculated by 2 in order to get the area of both of these regions, rather than have to deal with like negative numbers, like the negative square root of 3 bound. Alright, now that we have these two, what we can do is, remember, since if you have a negative area, you can just absolute value it. So this turns into 4 square root of 3. And that's the total area under the curve. So if you add 4 square root of 3 onto 4 square root of 3 minus 20 over 3, you get, okay, let's make some more space. You get, so if we add these two numbers together, plus, let's use a different color, plus, you get 8 square root of 3 minus 20 over 3. And this right here is your final total area for the absolute value of your function. So keep in mind, if there's tricks like symmetry, if the function's symmetric and you understand the function well enough, you can just do simple tricks like multiplying your areas you find by 2. But that's, of course, if you know how to draw the curves well enough. So for this function, you have a sine function. And if we were to just plug in both of these numbers using the fundamental theorem of calculus, you would just get total area, or a net area, sorry. Let me use the proper wording, a net area of 0. And if I were to draw this graph out to help you visualize that, a sine function looks something like this. And from 0 to 2 pi looks like this. So you can already get where I'm going. The area here and the area here are symmetric since this is a trig function that doesn't have any like adjustments along the way. And these areas are equal, therefore this is a positive and negative area that are equal. Add them together, you get an area or total area of 0. So what can we do? Well, first things first, let's go ahead and find the zeros of your sine function. So sine is equal to 0 when x is at any location from 0, pi, 2 pi, 3 pi, just any number n pi. But we only want to care about the zeros that are within your bounds. So what 0 is within your bounds? In this case, pi. Like 5 pi will be all the way out there. Like, I don't know, maybe like, if I were to make more space. 5 pi will be right here, and we don't care. Oops, I drew that bad. We don't care about what's all the way out this far. It's not even within your integral that you're trying to solve. So you want to keep in mind that whatever zeros you find for a function has to be within your bounds. So it has to be between the bounds of your integral, 0 and 2 pi. And pi is the only number that is between 0 and 2 pi, where it meets the condition of sine of x is equal to 0. Let's put that down here. And let's go ahead and find the antiderivative. Always useful for integrals. And the antiderivative of your sine function is equal to negative cosine of x. So we're going to use that for our calculations. And what we're going to do, again, is separate our integrals into two different integrals. So now that we have the 0 for your function, pi right over here, we can write the integral 0 to pi for sine of x first. And that's equal to, well, negative cosine of pi minus cosine of minus negative cosine of 0. There you go. So when you solve for this, you just get negative 1, since the cosine of pi is negative 1, you have a negative leading here as well, minus negative cosine, which is cosine of 0 is 1, so you have negative 1 here. And all these negatives actually cancel out. So you just end up with 1 plus 1. So the area for the function sine between 0 and pi is simply just 2. And remember, since we have a symmetric function here, well, we could just multiply your area you found here by 2. When you multiply by 2, you get this area as well. Now, if you don't understand what I meant by that, here, let's write down absolute value 4. So we already have the answer 4 if you multiply by 2. But if you want to solve with a more analytical method, again, you can just separate the integral into two regions, pi and 2 pi. And what we expect out of this is a negative area since the function is below the x-axis. So if we plug in negative cosine of 2 pi minus negative cosine of pi, we get negative 1, since the cosine of 2 pi is 1, and we get negative minus negative 1, since the cosine of pi is negative 1. So right here, this negative cancels out to give us a positive 1, but now it's just negative 1 minus 1, which is equal to negative 2. And negative 2 is the net area of this region. But if we have to absolute value it, remember we're trying to find total area. So we absolute value this, and we just get an area of 2. So you add these two together, and you still get 4, which was our answer initially by just multiplying this region by 2. Now, let's cover a couple other things that will make your life easier when you're calculating for total area. if you find the zeros of your function, right? But the x values of your zero don't lie within the bounds of your integral, you can just solve the integral normally using your fundamental theorem of calculus. That means, so if the bounds of your integral do not have any zeros of your function between them, then you don't have any negative area. So if I were to draw this out, so let's say for the function x cubed for this example, 1 and 5 here, if the only time when this function intersects with the x-axis is at x equals 0, but we just cared about solving the integral from 1 to 5, then we wouldn't need to do any absolute value or anything like that because the total areas are already positive. So if your function does not intersect with 0 at any point, and you know that you have positive values between 1 and 5 for your function, then you don't have to worry about doing any absolute value or net area or anything like that. Just solve the integral like normal. So what if you had some function that intersects with 0 as well? So in some cases, of course you need to do some testing, but in some cases, your function will intersect with 0 right here, but it won't go negative. So in some cases, your function will intersect with 0, but it won't go negative. So these are the things that you have to either draw out or maybe use a sign chart to solve. The sign chart would be quite helpful in this case, since if you see like a sign of like, if you saw like, let's say this function intersects at 0 at x equals -1, you have -1 here. If you just saw positive on your sign chart for your function f of x, then that means you don't even go into negative area. So you can again solve the function like normal. Sorry, solve the integral like normal. You don't have to do any absolute values or anything like that since everything's already positive. But as always, if you have any questions, put it down in the comment section. And if you found this video helpful, consider subscribing and liking the video. Thanks for watching.